Continuing where we left off on Monday. Quite frequently, one of the problems with this is that the algebra is the sucky part. In example 3 here on page 961, and I'm just going to set it down here instead of actually going through the whole damn thing. The issue is that we end up with this equation x to the 9th minus x. So if I factor an x out of that, I have to factor x to the 8th minus 1. That's a difference of squares 3 times to get it to where it's actually factorable. And I end up with 3 x values that work. X being 0 and x being plus or minus 1, because these don't have any roots in the real numbers, which means I end up with 3 critical points. Because we got here that y is x cubed, so 0 cubed is 0, and 1 cubed is 1, and negative 1 cubed is 1. So I look at those 3 points, and I'll do the second derivative tests. And there are my second derivative tests. So when I put in 0, 0, I get negative 16. And when my second derivative test gives me a negative, that's a saddle point. If I put in 1, 1, I get this being positive. It'll be 144 minus 16. If I put in negative 1, negative 1, this is again positive, 144 minus 16. And notice that fxx is always positive. So that means that it's going up. I have a local minimum. So I have a minimum at 1, 1, another minimum at negative 1, negative 1, and a saddle point at 0, 0. Now, I could graph this in 3D, but the textbook actually gives me a contour plot. And looking at the contour plot here actually gives me a useful piece of information that I didn't expect. I see the extremes at 1, 1 and negative 1, 1 as concentric rings. And that makes sense. We're going up or we're going down like our paraboloid did, right? Clearly, this isn't a paraboloid. It's got other crap going on. But here in the center, I actually have a crossing point on my contours. It's a little difficult to see because the contour actually comes around. It's right here. It's very, very difficult to see. This contour hits the y-axis and goes straight and comes out here. This contour hits the x-axis, goes straight and comes out here. The contours cross at the origin. And because the contours cross, that crossing point is my saddle point. Which means I can just look at a contour plot and tell you about maximums, minimums, and saddle points, even knowing nothing else about what's going on. By the way, there's the picture in 3D. Looks like a pair of trousers with no holes for the legs. But there are our minimums, and there's our saddle point. And you can clearly see the part that goes down and the part that comes up. So I've got exactly the saddle I was expecting. The down is going diagonally, and the up is going diagonally the other way. But even if I just give you a contour plot, you can tell me things just by looking there. Page 964. Here's a contour plot. I have not anything written down here about what the function is or what it's doing. But tell me, how many maximums or minimums do we have? I see 3 points where I've got that concentric ring behavior. Now, I don't know off the top of my head whether the maximums or minimums until I look at the labels on the contours and I see locally 0.837, this is going up. So these, by symmetry, I'm going to assume this is also going up. These are maximums locally. I don't have a value here except I got 1.48 and then I've got negative 0.8 to either side of it. I got a 3 here and a -1. I think this is also potentially a minimum, potentially another maximum. I think it might actually be a maximum based on that set of numbers there. How many saddle points do I have? I've got 2 of them, one here and one here. And we can even see if this is a maximum and this is a maximum, then this line would be an upward curve and we'd be going down in this direction. If this is a maximum and this is a maximum, I have that up behavior and the down behavior perpendicular to one another. Now, again, I can get a 3D drawing of this. Once I go back and actually look at the 3D version, I do see there are 3 local maximums and 2 saddle points. No local minima. But I'd have to run all of my critical point tests and my second derivative to see that that's what's going on. This particular problem, to do the algebra, they actually threw it in the computer. The algebra is that disgusting. I see nothing wrong with that. I can solve these numerically, plug them in. Let's go for it. This application, this sounds exactly like something we did in Calc 1. Here's a box. Let's make the maximum volume of a box. Remember that? We optimized. Well, now I'm optimizing without any restrictions on the relationship between the length and the width and the height, right? We had, oh, the volume must be a particular size, the base must be twice the width. We had all those restrictions. Well, now I don't have any of that. It just says total surface area is 12 square meters. Oh, well, front and back, each set is a rectangle of Y and Z. This left and right side are X and Z. And then the base is X, Y. I only need one of those because it's an open top. So there's my volume function. So I can use this, solve for one of the variables in terms of the other 2, turn that into a function of 2 variables. And then I have the volume now. I want to find the maximums. So a lot of these are problems we've done and can continue to do. But one thing I haven't done so far is talk about absolute maximum and minimum. So let me ask you the question from Calc 1. When we were looking for absolute max and min, how did we change the problem? There were 2 different ways to find absolute maximums and minimums. But I'm using my second derivative here, so that's not a change to me. And I only use the second derivative sometimes. Sometimes I still used the first derivative. We did something else. We added something to the setup of the problem. We added an interval. So, for example, that closed interval there guaranteed me that I would have a maximum and a minimum absolute behavior. Why? Think about the shape of this function. X cubed, right? But it can't keep going up forever because I chopped it off at x equals 3. and it can't keep going down forever because I chopped it off at x equals -1. So I've given myself a finite section of the graph. You have to have a highest spot and a lowest spot in a finite piece. So in this class, I'm going to make that same claim. I have to have an absolute maximum and a minimum when I have a bounded part of my graph. So I have to include a bounded region. And then in Calc 1, we would find all the critical points. And we'd only care about the critical points that were in my bounded region. And then we would check the edges of the region. I want to do the same thing here. So my procedure is the same idea. Find the critical points in the region R, and then find z values for those. And this is the important part. I have to check the edges of my region. But checking the edges of my region, that's actually Calc 1. Because each region will be an interval. An example. Otherwise, it's just me flapping my face. I would like to find the maximum and minimum values of this function, x squared minus 2xy plus 2y, on the rectangle from 0 to 3 in x, from 0 to 2 in y. Now, it turns out that it is not required for me to use a rectangle, but if I want to do this on a shape that isn't a rectangle, it's a lot harder. So I'm not going to at this point. If you're more interested in that, there's something called the maximum modulus theorem, comes from complex variables, being taught by Dr. McNabb this coming fall. This, of course, is the appropriate prerequisite. Okay. Start with step 1. Find me the critical points. Now, the region I've chosen is a closed region. It includes all of the edges. X goes from 0 to 3 inclusive. Y goes from 0 to 2 inclusive. So I have a closed region, like a closed interval. And it's bounded. It fits inside some circle. In this case, really easy to say, oh, it's in here. Such a region is called a domain. And the real requirement for me to be able to do this is that I'm working on a domain. For now, I'm sticking with rectangles. We'll figure out other domains later. How do I find the critical points? So partial with respect to x. And partial with respect to y. Hey, wait a minute, that's only in one variable. So if fy equals 0, that means that x equals right? I get minus 2x equals minus 2. I divide, I get x equals 1. And then I can put that over here and I can say for this to be 0, x has to be 1. What's y? Y is also. So the only critical point is the point 1, 1. Now, that could be a local maximum, a local minimum, or a saddle point. But here's the sneaky part. I don't care. Because I know I have to have a maximum, I have to have a minimum on this bounded region. It might be this point. But all I need is the z value for this point. What's the z value for this point? One minus 2 plus 2 is 1. If you wanted to, you could, right here, next to this, write the number 1. That's our z value. But all I need to know is I need to remember that z value. Now, here's step 3, the hard part. I need to look at each and every edge. I need to consider the boundaries of my region. Now, normally back in Calc 1, all we would do is we would plug in those numbers. But I can't plug in every number along this whole side, or this whole side, or this whole side, or this whole side. That's a pain in the ass. So we need to check each side of this rectangle separately. So I need your help. Where are we going to start? Which of the 4 sides? Left, bottom, right, top. Okay. Which way are we going to go? Clockwise or counterclockwise? You said start at the top, so this is side 1. That means this is side 2, this is side 3, this is side 4. So, what do I know about side 1? What do I know about all the points on that side? Aha. And that means that my function, I can put in 2 for the y value. Which means this is now a function just in x. Take that function, put a 2 in for every y. And I know x is between . So now I'm going to ask you to go back to Calc 1. And let's find the maximums and minimums of this function on this interval. Say that again, Mia? I gotta do this 4 times. This is the sucky part, that I gotta do this 4 times. Oh, well, I will learn to live with my disappointment. Okay, wait a minute. I know how to do this. To find the absolute maximum and minimum, I take the derivative, 2x minus 4. I set that equal to 0. And that's true at x equals 2. And then I say, oh, x equals f of x equals, and now I take the ends, 0 and 3, and I take the critical number in the middle, and I plug them in. What happens when you put in 0? When you put in 2? What happens when you get 3? Nine minus 12 is -3, plus 4 is 1. Okay, but remember, all of these have y equal to 2. So really, the point 0, 2 has the z value 4. I'm sorry, the point 0, 0 has the z value 4. The point, no, I was right the first time. They all have y equals 2. The point 2, 2 has 0, and the point 3, 2 has 1. So far, so good. 3 more sides to go. Now, again, I could put these numbers on the drawing in the spots, right? Because now I have a critical point here, and here, and here. 0, 2, 2, 2, and 3, 2 are those 3 dots. What do I know about side 2? X is 0. So I repeat this same process. Which means my function now becomes a function of y only. So I take my function, remember f of x, y is x squared minus 2xy plus 2y. I put in x equals 0. What's f of y? Two y. Hey, wait a minute, that's a straight line. So the maximum and minimum have to be at the ends. There's no critical point. So I can skip this part because I know f prime is never 0. F prime of y is always 2. So the only numbers I have to check are the ends. Wait a minute. What are the ends of this section? Side 2 is here. So the ends are 0 and 2. I didn't write that down up here. I should write that up here. With 0 less than or equal to y less than or equal to 2. Fill in the numbers. That's easy. Hey, wait a minute. Remember, x equals 0. So the points are 0, 0, and 0, 2. I have a z value of 0 and a z value of 4. This number is the same as that one. Good. I got the same answer 2 different ways for the height there. I feel better. Now I've looked at this edge and this edge. Time for side 3. I got to go back to the other picture. What do I know about side 3? Y is 0. So f of xy becomes f of x0, and x goes from 0 to 3 across the bottom of the rectangle. Okay, wait a minute. What's f of x0? Put in a 0 there. I put in a 0 there. So I take the derivative. The only critical number is 0, which happens to be one of my n's. So I only have two numbers to check this time. So again, I can say y is 0. At 0, 0, I get 0. And at 3, 0, I get 9. One last side. Side 4. What do I know about side 4? Be careful. X equals 3. That's a vertical side. It's x equals. And again, that's with 0 less than or equal to y less than or equal to 2. I need to put together my function. So I put in 3 and I get f of 3y, which will be f of y. And that's 9 minus 2 times x times, 2 times 3 times y, plus 2y. Now, wait a second. Once again, f prime of y is a constant. So the only places I need to look are the edges. Plug in 0, plug in 2. Okay, wait a minute. Plug in 0, I get 9. 9 minus 8 is 1. So at the point 3, 0, I have a height of 9. That matches. And at the point 3, 2, I have a height of 1. Okay, wait a minute. We did 3, 2 during side 1. So let me go back to the picture. I'll redraw the picture just for the moment. 1, 2, 3, 1, 2. Here is my rectangle. We had a critical point at 1, 1. We found the point, let's see, 0, 2, 0, 0, 3, 0, 0, 2, 2, 2, and 3, 2. And then there was nothing on those vertical edges, right? Those are the points we came up with. All of the points from all of the sides and the critical points. We had a height of 1 here. We have a height of 3, 0, 9 here. We have a height of 1 here. We have a height of 0 here. 0, 2, we had a height of 4 there. 2, 2, we had a height of 0 there. 0, 0, 2, 2, 3, 2. 0, 0, 0, 2, 0, 0, 3, 0. Oh, this is not a point. This is a mistake. Never mind. Now I know. Where's my maximum? Here. Where's my minimum? Here. Which means this shape, just from looking at these numbers, this shape goes down in this direction, goes up in this direction. This is a hyperbolic paraboloid. But instead of taking the whole hyperbolic paraboloid, I took a piece of it. And I got a high corner, a not quite as high corner, a low corner, and a low corner.
So you go to one mode,
From here to here.
that's still sun.
Ah, but notice the straight line is this way, right? This side is a little higher because it's going more towards this direction. So it's going down this angle and it's going up this way. So this is higher than that because this isn't a square. This is a rectangle. So it's lopsided in one direction, isn't it? My maximum value is 9, and it occurs at the point 3, 0. And my absolute minimum value is 0, and that's at 0, 0, and 2, 2. I would like to point out that this one problem took about 20 minutes. This is substantially harder because I have to check all of the different edges involved. Now, if I want to do this in some region that's not a rectangle, then I'm going to have to figure out how to take my derivative on a curve to find a maximum and a minimum. Well, that would be taking directional derivative, right? Ugh, that's much more complicated. I don't like that at all. Even if I could make a nice simple region like a circle, then I might have to try and do this in polar coordinates. Yeah, I agree. Blah, it's disgusting. No, that's a horrible idea. But that is a restriction we run up against. This is very particular about working with derivatives in X and Y. So working on rectangles is much easier. Working in any other shape at this point is damn near impossible. So how do I fix that? Questions before I get to fixing it?
How does the saddle point look on that graph?
It's still the same sort of shape, isn't it? It's going down this direction and up this direction. But it just goes up higher in one corner than above in the other because it's not a square picture, it's a rectangular. So the corner that's nearest us at x equals 3 is much higher than the corner back here at y equals 2. So this corner is higher than this corner.
You can get an absolute minimum and max, but it's a saddle point.
I could, but only if that saddle point was on an edge, right? And it would still be very weird, right? Because if it's truly a saddle point, then it should be going down in the other direction, shouldn't it? So if the region includes stuff that goes that way, it should be lower. I would say you're probably right. I'll never get an extreme that is a saddle point. Oh, yeah, right. Yeah, look, took us 20 minutes to do this one. You only have 50 minutes. The exam has 3 problems. Let's go. Be like asking you to do the one with the giant x to the 9th power in it. That's the example in the text. Example 3. Yeah, the factoring will be forever. Come on. I'm a sadistic bastard, but that's beyond me. It is also possible to have critical points that aren't isolated. Now, that's a term I haven't used yet, but let me see if I can make it make sense. An isolated critical point is the only critical point in a small section in a disk, right? This point is the minimum in that, or is the value in that area. This is a saddle point. It's the only critical point in that little circle. But here, I wrote it down. Where's the example? This one. F of xy equals 1 plus 2xy minus x squared minus y squared. Now, I'm just going to ask you for global, local, not global. I'm going to do this whole problem without a box. Well, let me take a look at what happens just in general for this one. I need to find the critical points. Partial with respect to x, partial with respect to y. What do I get? Partial with respect is, with respect to x. Partial with respect to y. I need to set both of these to 0, right? So I'm going to rewrite one of these to switch the order. I'll rewrite fx as minus 2x plus 2y. But if I set fx equal to 0 and fy equal to 0, then I get the simultaneous equations that look like that. Simultaneous equations were a long time ago, or they were last semester in linear algebra, or last year in linear algebra. What's the problem with this? Which means when I go to solve this by elimination, I get 0 equals 0. Which means that this actually has infinitely many critical points. As a matter of fact, if I think about minus 2x plus 2y equals 0, I can make that 2y equals 2x or y equals x. The entire line y equals x. Every point on that line is a critical point. What the? What? Every point on the entire line is a critical point. Maximums, minimums, saddle points, what are they? Let's do the second derivative test. Fxx, fxy, fyx, fyy. What do I get for these? There, now I can see everything at the same time. Which means D is fxx times fxy minus fxy squared. Wait a minute, that's 0. What does that mean the second derivative tells me? Based on what we did Monday.
That doesn't help.
So you. Thanks, man. Okay, wait a minute. I need to figure out what's going on here. But this graph has an entire line of critical points. If they were saddle points, then everything that went across this line would have to be going up in one direction and down in another, right? That doesn't make sense. I can't figure out how to make that happen across the whole line. So maybe these are all minimums. And I could have something that looked like a parabolic cylinder. Or maybe they're all maximums. Same idea, parabolic cylinder, right? So I need to go back and figure out what this function f of x, y, what this thing looks like. So I can do this in several different ways. I can graph it. But I can also do a little bit of sneaky algebra. Let me go back and look at that function algebraically. F of xy equals 1 plus 2xy minus x squared minus y squared. And I say to myself, I hate having negatives with my x squared and negative with my y squared. But the fact that those are both negative says to me, I think we should be going down. So I'm going to factor out a minus sign. And I'm going to write this as 1 minus. What would go inside that set of parentheses if it was 1 minus? So let me write it as x squared minus 2xy plus y squared. And all of a sudden I say, wait a minute, I know that pattern. That's a square. This is 1 minus the quantity x minus y squared. 1 minus something squared, that's a parabola that goes down, isn't it? So now if I actually do look at the graph, I see this thing. And my reaction is, what the hell? Until I turn it. And there's my downward opening parabola. At an angle of 45 degrees to the x and y axis. It's a parabola along the line y equals x. Isolated critical points are alone. None of these critical points are isolated. They're all connected to one another in that line. Isolated critical points are a lot easier to deal with because my derivative test tells me something. In this direction, this graph has no curvature. This is flat along the line y equals x. That's why my second derivative gave me a 0 for the discriminant, because it isn't going up, it isn't going down, it isn't saddling, it's flat there. When my first derivative is 0, I'm horizontal. When my second derivative is positive, I'm curving up. When my second derivative is negative, I'm curving down. When my second derivative is 0, I'm not curving. My graph is a straight line. And in this case, it's the direction in which it is a straight line that is told to me by this information. Son of. So here's a case where I would have a whole lot of different kinds of reactions depending on where I cut this, right? I could get minimums on one side, I could get minimums on the other side. I'm never going to get a saddle point. There are no saddle points in this function. I could get a maximum if the section I cut contains that line, a maximum height of 1. Okay. I would like to fix this problem of being only able to maximize or minimize on rectangles. I'd like to be able to maximize or minimize based on other restrictions, or at the very least, optimize based on those other restrictions. So I need a more general method. That method is what I'm going to do tomorrow, called Lagrange multipliers. So we'll talk about that tomorrow. I will see you all.